Hello everyone, welcome to today's tutorial on work and energy with varying forces. So when we have a spring and we apply a force, we notice that there is an extension, and this force is given by kx, as we have done in simple harmonic motion. This is the equilibrium position. So this is x in the negative direction, if you like, or if we take down to be positive, it is positive kx. Then on the wall, actually a force is exerted, which is minus kx on the wall or on the ceiling. If we keep on increasing this force, we will see that the extension will keep on increasing. And then if we plot a graph of this variable fx force as a function of displacement x, we can get a curve that looks like this. So in order to find the work done by this force, we basically have to divide this curve into small segments and use it to form strips, so that we can easily make it look like a rectangle. So let this point be xa and this point xb. So it means that the distance between here to that place is sb minus xa. And let us assume that this distance is x1, delta x2, delta x3, delta x4, delta x5, delta x6, delta x7, delta x8. So it means that the work done by this force, so it means that here will be on this axis, if you like, f1, here if we extend it, f2, and so forth and so forth, f3, f4, f5, f6, f7, f8. So it means that this force moves this x from this point to this point, the other one moves from x from this point to this point, and so forth and so on. So we can calculate the work done by F to be equal to the sum of the area of each strip plus F3 delta x3 plus T, we get to F8 delta x8. So that if we make delta x to tend to 0, that's if we make this strip tinier and tinier, and many of them, we will have that in that limit, in the limit of this tending to 0, it means that our W will be equal to integral xa from here to xb of fx, the x. That's what we will have, where this is a variable force. If this force is non-variable, let's assume that it is constant, you will expect something like this: force fx, f if you like, or fx. So the area under the graph will also be the work done, just like the area under this curve is the work done. So here is our SA xb. So it means now, for a constant force, it means that the work done will be, since fx is constant and is equal to f, we bring it outside, the x from A to B for constant force. And it means f, if you x within the limit of xa to xb, and that is f xb minus xa, and is equal to, let's call it a capital X from here to here. From here to here, capital X is equal to F capital X. This is for constant force, while this is for variable force. What it now means that for this spring, we now know that our kx, so if we substitute it in the work done, we will have for the spring is equal to integral, our fx is kx dx, so that and it moves from equilibrium position to x, if you like. Let me put it capital X also, so that we have capital X here, so that you have, if we differentiate this, you have 1 over 2 kx squared 0 to capital X, and that is equal to, that's equal to 1 over 2 kx squared minus 0. So that is what you will get, and this is just the area. So it means that we'll have something like this, fx and x. So this is fx is equal to kx. So the area, so let's assume that is somewhere here. So here is 0 and here is x, capital X. So and here is the kx, fx kx. So it means that the area, the work done is the area under this graph, this right angle triangle, and it's the area under the graph is equal to half base times height. So have half x times height is kx, so have half kx squared. So we confirm that that is correct. Graphically, this is how to do it, but if we do it using iteration method, that is what we will have. Okay, what this thing is just telling us is that the work done is equal to the product of the average force and the displacement. The average force here is kx is the force, average force is this, then times displacement, so that we have half kx squared over 2. You can also see that the work done, W, is proportional to the displacement squared. It is proportional to the displacement squared. That means that if we stretch our segment by 1 cm, the work done will be 1 over 2 k 1 squared. And if we stretch it by, say, 3 cm, you will see that the work done will be 1 over 2k into 3 squared. So the work done will be 9 times when it is stretched by 1 cm. So if we do it by 4, if we stretch it by 4, we will have 4 cm, we will have 1 over 2k 4 squared. So it will be 16 times when it is stretched by 1 cm, and so forth and so on. So let us do an example. Let us assume that in a bathroom, there's a scale in a bathroom. Let's say a scale in a bathroom. You know that a scale is made up of spring, but only that it is moving downwards. It's compressed and not elongated. It is compressed. So let's assume that a noisy mother climbs on that bathroom scale and depresses it and compresses it by 30 millimeters. And let's assume that the weight of the woman or the noisy mother is 650 Newton, and immediately her toddler, that's a child, has started crying, and the father hands the toddler over to her. You know that the weight will increase. Immediately the thing was handed over to her, the x2 becomes 15 millimeter. So we now want to find, one, the spring constant. 2, the work done on the scale by the nursing mother. 3, work done on the scale by the woman and the toddler. And if you like, 4, the weight of the toddler. In order to do this, what we will have to do is to remind ourselves of Hooke's law. And Hooke's law states that force is proportional to extension, or force is proportional to compression. F is equal to kx. That means that our k is equal to F over x. So, but our force, because if we draw the free body diagram, you see that this is the equilibrium position. The x will be here because it will be depressed, and the weight is acting downward. Force is going down. Force is negative, is equal to minus 650. Minus 650 Newton. And this is x coming down this way from equilibrium position. So it means that our F is negative because it's coming down 650, and our X is compression. If here is our negative Y and here is our positive X, which means positive Y, negative X. So this is a minus 13 times 10 raised to the power minus 3 meters. So, and that will give us approximately 5 times 10 raised to the power 4 Newton per meter. So the force constant for the first one is that. So the second one is initially it was at equilibrium position, and from what we have been doing, the work done will be half kx2 squared minus half kx1 squared. And x1 is 0 because it's at equilibrium position, so we'll have it to be half 50,000. X is equal to minus 13 times 10 raised to the power minus 3 meter all squared. So it will be positive minus the whole of this is 0 because x1 is 0, approximately 4.225 joule. So when the toddler was handed over to the woman, we will have the same formula: half times 50,000 times minus 15 times 10 raised to the power minus 3 meter squared minus 0, and you will get about 5.625 joule. We can from here find the net work done by the toddler. You either say this minus this, 5.625 minus 4.225, and you get it to be 1.4 joule. Or you can just say net work done by toddler, WT, is equal to half 50,000 times minus 15 times 10 raised to the power minus 3 meter squared minus the one done by the mother alone. That's what you write, times 10 raised to the power minus 3 meter all squared, and you find out that is equal to 1.4 joule. So D, to find the weight of the toddler, we have seen force constant K is equal to also, so it will be equal to, since it's a constant, so it's equal to 650 plus the weight of the toddler all over minus 15 times 10 raised to the power minus 3 meter. Find out that WT, the weight of the toddler, is because it's pressing down, so it's actually plus minus is minus 650, so that you see that this one will cancel this one will give 550. 50 plus times 15 is 750 minus 650 Newton will have 100 Newton. So the weight of the toddler is 100 Newton, or about 10 kg. So that is how to do this type of thing. So please subscribe and click on the notification button so that whenever we post new videos, you see them. Bye.